Howdy and welcome back. So other tree representations. Let's just do a review before we get into this. So we talked about, if our nodes within a tree can have, say, an unbound number of children. So not always presenting between 0 and k, but, some might have one, some might have 1,000, what have you. We see that kind of using this linked list data structure to have pointers of, from one sibling to the next might be advantageous in that scenario. We also introduced kind of this idea saying, well, maybe if we always had between 0 and k, so every node would have between 0 and k, maybe an array in that instance might prove advantageous as well. And again, there's a number of different performance implications that you'd have to consider, but if it's always between 0 and 3, an array might be, sensible in that interest. But again, you have to consider the trade-offs. If you're using a dynamically allocated array, and you maybe wanted to scale to exceed k, you're getting into this whole resizing and copying process that we saw when we implemented our pseudo vector. So in that instance, it might be better to take advantage of the singly linked list kind of implementation for this unbounding process. And that if we need to tag on an extra child, there's no resizing that needs to be done if we're at capacity. We just tack it on to the end. But again, you're going to get into kind of some more of these trade-offs between, something like this, which would be good for maybe a bounded implementation where k is small and utilization is high, against, say, this unbounded, this for a unbounded implication when k varies drastically across the different number of nodes. So there are many different ways, different schemes we can use with different trade-offs to represent tree data structure. Some trees, and one example of this is what I'm going to point out now, is that some trees are traversed only towards the root. So from the leaf to the root, or from a child to the root, and therefore they only maintain parent pointers. There are no pointers to the children. You'll see this with when you start talking about maybe union sets in 225. We could also store a binary tree in an array instead of a linked list. So you will definitely encounter this in 225 when they introduce the binary heap data structure. So let's kind of look at this, and we're going to use the actual location of the element within the array, so 1 through size, opposed to looking at this from the perspective of the indexes, which would be 0 indexed. So I, in this case, is going to refer more to position than it is index. So at position 1 within our array, so at index 0, we could go ahead and store the root of our tree, 16. The left child could be stored at position 2, or index 1. The right child could then be stored at position 3. Now here's where kind of these the implications of these multiples of 2 comes out in this bound number of children at 2, is that the left child of any of these nodes, given their position, will always be at 2 multiplied by the parent's position. So for the left child of the element at position, find the purple, at position 1, storing the integer value of 16, its left child would be at slot or position 2 times 1, so position 2 or index 1 in the array. The right child would live at, let me go ahead, highlight this, would be at the parent's position, so 1 multiplied by 2 plus 1, so the third position in our array, or that at 0 at the, second index. Okay, so what if we wanted 3's parent? We could simply divide its position within our array by 2, and this is integer division in C++. So 3 divided by 2 is going to give us 1. So at that point, we know that the parent resides at position 1. Likewise, the parent of the element occupying the second index over here, parent would reside at its slot 2 divided by 2, which would give us position 1. And again, this is all taking advantage of the integer arithmetic. Likewise, if we wanted to say find 10's left children, we would multiply 3 by 2, which would give us the 6 index into our array. Find a color for this. And lo and behold, there it is. Likewise, if we wanted to find 10's right child, it would be 3 times 2 plus 1, which would give us to the 7th. Oops. The 7th position in the array, or that at the 6th index. So just using these offsets provide a interesting way to kind of navigate through this array to find, say, the parent and children of the respective elements of the tree encoded within the array. And again, you'll get more into kind of the advantages to, well, I guess first, what a heap, binary heap data structure is useful for, as well as the implications of storing it within an array and the utility thereof within 225. So without ado, we're done for the day. I hope this lesson was informative, and we'll move on to our binary search trees tomorrow.